All right. So the homeworks are up here. If you need to get them, just try not to disturb the lecture as we do this. But today is exam review day. Yay. That's the kind of attitude I like. But you can't see it yet. Source. Laptop. We've got to plug it in before we can do that. Plug this in. Good. And okay. Awesome. Exam review day. You can expect the exam to be about 75% short answer or true, false type questions. Very small, couple of word answers. 5% sentence, single sentence responses. And then the remaining 20% will be some kind of coding problem. I can draw from the homework topics, anything we did on the homework, everything in the assigned reading, because I had assigned reading every class, you all read it, and anything from the labs, anything from the lectures. Specifically, all of this encompasses chapters 1 through 6 inclusive. Nobody move. I panicked. That is an emergency exit door, by the way. So you should feel really good that I can't open it in the event of an emergency. So chapters 1 to 6. Everything else today's lecture is just whatever you want to talk about. I will write any piece of code, any macro. Doesn't matter if it's from the lab, from a homework, from something you read in the book. Things that you are allowed to bring. You must bring your ASM sheet. Okay? I'm not going to provide it, but you can bring it. And you should bring it, because otherwise you're going to be screwed. So bring your ASM sheet. No calculators are needed. Okay? So bring your ASM sheet, no calculators. You can have one single-sided 8.5 by 11-inch piece of paper as a cheat sheet. Okay. Is there anything else anybody wants to bring? Want to run it by me right now? That should be all you. The register summary. You really don't need it for this, but you are welcome to bring it as long as it is unmarked up. There is on the M drive a register summary. I will show it to you right now. M drive 263 manuals register summary.pdf. The register summary.pdf is just, port D, port C, tells you what the names of them are. So you can bring that. This will become much more important on exam 2 when we start talking about this stuff. All right. But it does have things like the status register, the stack pointer high and low, things like that. So you can bring that in the M drive, print it out if you so desire. Okay. But really all you should need is the ASM sheet, single-sided cheat sheet, and you'll be good to go. Any other questions about the content or form of the exam? No. All right, so the rest of the class, the remaining hour and 10, is whatever you want to talk about. Okay, right there. Which one? Copy memory from one place to another and create a checksum, right? Create a sum. Is that what it's supposed to do? All right. So let's just agree on what it said. Copy memory locations 110 through what was it? Through 180? Yeah, okay. So it was from 110 to 125 to 180 to 195, right?
Copy 110, copy numbers starting at 110 to starting at 180.
Okay, so the block starting at 110 onwards to the block starting at 180. 80. How big is this block? 25 bytes. Okay. All right. Well, for me, the basic approach would be to build up a loop. Okay. And the loop would say something like load from source into a register, and then store the register into the destination. Somewhere in here we have to increment a pointer, and then we have to make sure that we decrement our counter. This is high level. This isn't going to directly translate into code yet. So dec counter. Then, are we done? If we're not done, we come back up and do this. So that's the loop. If we are done, stop. So done, yes, no. What do we have to do before the loop? Well, we have to set up all of these values. So we need our counter to equal 25. We need source to equal 110. We need destination to equal 180. That's our initializer. And then there's a, so that's my basic outline that I want to follow. How many people follow along there or have a problem with that? I'm making it up as I go along, so it's perfectly possible that I'll make mistakes. Okay? Seem reasonable. All right. Well, now we got to do some register assignments. So for my purposes, I'm going to assume that counter is R5. I'm going to assume that source is X, destination is Y. Now X is really 31, 30, 29, 28, 27, and 26. Y is really 29 and 28 registers, general purpose registers. Okay, so I've got to deal with this. So I chose R5, and unfortunately I can't just do a load immediate with R5, can I? All right. I mean, so I kind of have to take the long way around. I know that I could do LDI with R16, and I can put 25 in there. Okay. Then how do I get R16 into R5? Move R5 into move R16 into R5 because data flows right to left. Left flows left. That was a joke, Gabe. You said right, and I said No, left.
Oh. That actually was a good one.
You're so disgusted.
That was so lame.
Wow.
What's wrong with you, man?
So lame. You know, Adam, that I don't write the exams until after I do this review session, right? All right. Anyway. Right. Left. Move.
Correct. If you said correct,
I could have said correct. Yeah.
there was no point. Okay.
It was very punny. All right. Can we continue? All right. Then we got to get 110 into x. Now, me being the lazy professor, I would prefer to just say LDWI XH XL 110. Get 110 into XH and XL. It's a fairly standard macro that we've had before, but I'll put it up here. Macro LDW. W meaning word. So load word immediate. And all we're saying here is LDI at 0, which is XH, high of the second argument here, 0, 1, 2. So that's at 2. LDI at 1, low of at 2. Dot and macro. Nothing like crazy about this macro. It's not even saving us that many lines, but it is making it look like one instruction. That's sort of the problem with assembly language, right? You can only do one thing at a time. But if we want to load up a word, we want to do it in one unit. So that's X, and then I can also LDWI YH YL the destination, $180. There we go. So that gets me R5, 110, and 180. Now I know that I've got a loop, so right here I'm going to call this the loop. And what do I have to do? I have to load from the source address and put it in a temporary register. What do we want the temporary register to be? R20. So this is going to be indirect addressing. It's indirect addressing because the instruction LD R20, comma X says the data is in X. But really what it means is the address is in X. The address in X points to memory, and that's where the final data is. So it's indirect addressing mode. So that loads from the source address, because X has 110 in it, puts it into R20. Then we want to store to the destination. So that's ST Y, comma, R20. The next step says increment the pointer. Which pointer? We've got two of them. Which one do we want to increment? If we increment X, let's go through this loop twice. All right, X and Y. X starts out at 110, right? Y starts out at 180. So we load from 110, we store to 180, then we increment X. Okay, now it's 111. So we come back up on the loop, we load from 111, and then we store to 180 again. Did we want to store to 180 again? No, we wanted to store to 181. So the correct answer is we want to increment both. Yeah, you know me. I do trick questions all the time. All right, it's a trick question. We want to do both of them because we want the pointers to move in tandem. All right, so that's incrementing the pointer. Incrementing the pointer means we got to increment both pointers, both the source and the destination every time. So this takes care of the increment by doing a post increment. It means it stores, then automatically increments. You could have said XL and increment XL, but that's not technically correct because it doesn't deal with the 16-bit addition correctly. So then we've got to decrement our counter. Decrementing is a dec instruction. The counter is R5. Decrement R5. Then we've got to say, all right, are we done? How do we know if we're done? Well, in this case, we've set up the loop so that we load our counter variable with 25. We can always use branch not equal, meaning the result of the previous subtraction was not 0. Think about that. Branch not equal means the result of the previous subtraction wasn't 0. So branch not equal back up to loop. And then finally, here, R jump here. Cover my face? No. I think that was the whole homework. All right. Now, could I come back and clean this up? Sure. There was no reason that I had to use R5. I could have used R16 the whole way. So I could have eliminated this line and just everywhere used R16. That takes out one line, one cycle. Other than that, that's about it. All right. This was just another example of iterating over memory. We've done a few different examples in class. Iterating and filling memory with a constant value. Iterating and filling memory with an increasing value. I think in the lab, I actually gave you load SRAM, iterates over memory and fills with a decreasing sequence starting at FF. And here, we copy memory from one place to another. Wasn't there more to this? Didn't you have to do a sum? Was that a different homework? Am I just forgetting that this existed? Or are you just all lying to me in a very clever hoax? All right. Well, that's, okay. Well, that's it then. That's the whole homework. Abe. What do you want to go over about macros? How to make them, how they work, or specific macros that might be helpful? Or yes, all of them. How to make them. All right. Anything that you write in code that you repeat fairly often is a candidate for a macro. All right. So one of the simplest things we did in chapter 4 was something like LDI R16, OX FF, and then we would out that to DDRB R16, right? Now, what are we really trying to do here? Set all bits of port D to outputs. That's what's really happening, right? Port B to outputs. That's what we're trying to do. So, and then we probably do it again for port D, maybe different values. And how would we do that? All right, LDI R17, OX F0 out DDRD, R17. This is the upper 4 bits are outputs. So this is something that we do, and it's virtually identical except for the arguments. So we could turn this into a macro. Macros are built up with 4 basic components. The dot macro directive, the dot end macro directive, the name. My personal preference is not to use long descriptive names, but to make it look like it was an assembly instruction. LDIO looks like LDI, but also has IO in it. Load immediate into IO. All right. And then the last thing is the body. Now the body is going to consist of exactly what we had in the top two examples. But if I circle things with some colors, those are the same. This is its own unit, and that's its own unit. So what I can do is, since these two things are the same, I can use the same positional argument. So how do I want to set up in LDIO? Well, for LDIO, it's going to be data flowing from right to left. So where I want the destination, I want this to be something like DDRB. I want the temporary register in the middle because it's both a source and a destination. And finally, OXFF. So this is going to be at 0. It's going to be at 1. This is going to be at 2. That's an at. So looking at this, this is at 1, at 1, at 0, at 2. So that's all I'm going to say. It's just, okay, load into at 1 whatever I gave for at 2. Then take wherever I'm going at 0 and deposit at 1 in it. So any piece of code that you see probably could be turned into a macro with arguments. Anything that you do more than once. When to do that is sort of a different question, because you could make this into a function, right? You could absolutely just call this, well, actually it gets a little bit more complicated. The nice thing about this is it does let you provide arguments. With a function, functions don't have arguments. You have to just assume that in a certain register things appear. The other downside of a function is you've got to call it, call function, and then you've got somewhere in your function some lines of code, and then a return. Now that call takes like 4 cycles. The return takes 4 cycles, I think. Check on your ASM sheet. Okay. So unlike this, which goes right in place, this has some extra overhead associated with it. The downside of the macro is every time you use it, it puts more in your RAM, or sorry, your ROM, puts more in your flash ROM because it copies the code. So it can explode your code quite a bit. Okay. Actually, you did have a question first.
Oh, I was just going to ask what the room we're going to test in there.
Yeah, you'll be across different rooms. So some of you will be in here, some of you will be in 214. There'll be a name sheet up. Yeah, okay, go ahead. No, timing is exactly the same. So if I said, instead of using these two options here, I just said LDI, DDRB, R16, OXFF, LDI, DDRD, R17, OXF0. These two lines each take 2 cycles because this takes 1 cycle, that takes 1 cycle, that takes 1 cycle, that takes 1 cycle. That's different from a call where the timing would be much larger. So the timing is exactly the same as if there was no macro.
Can we go over how to calculate the amount of cycles?
Sure. So let's make up a loop here. Oh, excuse me. L3, L2, decrement R17 branch not equal to L1. Okay, so that's, you know what? Let's do it like this. So that you can clearly see what's going on here. Okay, same code here, but at least this way it's all put together as one thing. Get rid of this stuff here. Same code. I've taken the liberty of putting some tabs in here, some spaces, to indicate where the loops are. This is a triply nested loop. So the first step is to identify the innermost loop. The innermost loop goes from L3 to the branch not equal L3. That's one loop. The next most innermost loop, goes from L2 to branch L2. And finally, the outer loop goes from the branch L1 back up to the L1. So we have 3 levels of loops here. Yes? Hold that thought. Let me actually move this over. Can you repeat that question?
Like the first inner loop, does it include the decrement R18?
Did I? No, 19, 18, 17. No, this is, I think, correct. 17, 18, 19, 19, 18, 17. Yeah, this is okay. Because think about this loop, right? You load up 19 with 100, then you decrement 19 until 19 goes to 0. Then you jump out of that loop, you decrement R18, and go back up and reload R19 with 100 again. Okay? So this is going to go R17, R18, R19. They're all going to get loaded with 100. And then R19 is going to go all the way down to 0. And then R18 will go to 99. R19 will get reset with 100, go to 0. And then this will go to 98. 98. This will go on for some time until they're both 0. Bug. And then 100 will become 99 in R17. So this is going to go on for some time, quite a while. So how do we determine this? First thing we got to do is figure out how much each line takes. LDIs are all one cycle. Decrements are all one cycle. Branches are listed as 2/ or is it 1/2 or 2/1? It's listed as 2/1 in your book. All right, 2/1. The 2 is the branch penalty. If it branches, it's 2. If it doesn't branch, so if instead of jumping back up to L3, branch not equal L3 jumped or fell through to the decrement, that would only take one cycle. Next, we got to do some math. So we're going to say, all right, the inner loop gets done 100 times. So the way I might think about this is the black loop is 3 times 100, because I took 1 plus 2, minus 1 to take care of the branch penalty. So that means every time this loop runs, it's going to take 299 cycles. Okay, but that inner black loop is going to be run multiple times inside the red loop. So how many times is that going to get run? So we add on to this. We know that now this LDI, which is inside red, that's going to get, let's actually, can I change one thing here? I'm going to set this guy to be 10, this guy to be 100, and this guy to be 200. That way it's different numbers all the way through, so you'll be able to see what's going on. So now instead of 3 times 100, this will be 3 times 200 minus 1. All right. So now this 1 is multiplied by 100. These are multiplied by 200 here. All right. So that way everybody knows what's going on in terms of which number is which. Meanwhile, this inner loop is also going to be executed 100 times. Now, we already figured out that that's going to be 3 times 200 minus 1. The decrement gets run 100 times. And the branch not equal gets, excuse me, that should be multiplied, gets run 100 times. So all told, if we look at each of the groupings, this is going to be 100. This is going to be 3 times 200 minus 1 times 100. Another 100, and this is going to be 200 minus 1. That's the red loop. Keep going here. Get rid of this stuff. Okay, so now the sum of the inner red loop is going to be, let's see, 100, 200, 400, 400 plus 600. Well, we can't do that yet. So that's 400 minus 1 plus 100 times 600 minus 1. So keeping this simple, that's 400 minus 1 plus 6 with 4 zeros, 60,000 minus 100. Okay, we can easily get rid of that minus 100. So that's now 60,000 plus 300 minus 1. And that's the sum of the red loop. But that red loop is going to run multiple times. So we now know that this is the time it takes every time this red loop runs. So let's look at the green loop. The green loop, this is going to execute how many times? 10 times. Each of these is going to execute 10 times. Then the whole red loop is going to execute 10 times. The decrement is going to execute 10 times. And the branch not equal is going to execute 10 times. So that'll be 10 times 2 is 20 minus 1. So now we have to take this whole thing, multiply it by 10. Well, what is that? That's going to be 10 plus 20 minus 1. That takes care of everything but the inner loop. Plus 10 times 60,000 plus 300 minus 1. So expand all that out. That's going to be 600,000 plus 3,000 minus 10. And then over here we still have 10 plus 10 plus 20 minus 1. So that's, well, we can cancel one of those 10s. So now we have, running out of space here, 600,000 plus 3,000. Where are we? Plus 30 minus 1. Am I done at this point? Have I dealt with every single line? What's the line I missed? The very first one. This isn't part of any loop, but it still adds one cycle, which conveniently means that we can cancel that. So what is our final answer? 603,030. Yes?
I think your
Face is covering things. Let's, oh, where's my pen? No, don't move that. That's a terrible idea. Just this stuff. Take this over here. Okay. There we go. So that's what was covered was 10 plus 10 plus 20 minus 1. That's the stuff in the green loop that isn't super nested. That's the simple stuff. So all I did was identify the formula each time. So the black loop had that as its formula. The red loop did have this as part of it, but that was multiplied by the number of times the red loop ran, plus the stuff that was around the red loop. Those lines here were part of the red loop. Then I figured out, all right, that's the whole red loop. And then I figured out the green loop by saying, all right, the green loop runs 10 times. And there's how much the red loop costs. So that's 10 times through the red loop. Sorry, 10 iterations of the red loop. And then this stuff is what remains in the green loop. Got to load it up 10 times, got to decrement and branch not equal 10 times. Every time we have a branch not equal, you got to account for that branch not equal. And it's always easier to not do the math. Imagine if instead of writing 600, I had written 599 here. 599 times 100, yeah, you can do that. But then that fits in here, and then so nothing cancels nicely anymore. Always just expand it out. Here it became 60,000 minus 100 instead of 59,990. 59,900. Okay? It keeps the math simple right up until the very end. As long as there are nice numbers here, right? Which, since there are no calculators, I'm going to give you nice numbers. Okay? I want you to be able to do the interesting stuff. The interesting stuff is what happens over here, not the multiplication. Okay? I don't know. You had a hand up. You were kind of going,
For the red loop, if you look at that front equation to the left, you have 400 minus 1 plus 100 times 600 minus 1. Now that 400 is what's got me confused.
Okay, here's how I came up with the 400. Ready? That plus that plus that. Everything that isn't the black loop, isn't that these are the 3 lines in the red loop. That's 4. Each of those lines runs 100 times. So that's where the 400 comes from. And then the minus 1 is because it is a branch penalty. So it would be 200 times, it would be 2 times 100 minus 1. So that's 200. This would be 100, that would be 100. So all told, it's 400 minus 1. I did something not quite the same. Here, I put it off all on the side. I could have said, all right, 1, 2, 3, 4. 4 times 10 is 40 minus 1. But I knew that in a little bit I was going to have that 10 and it was going to disappear. So I just left it like that. All right. But I could have said 40 minus 1 and then it would have been 30. Okay. And never forget this first line, even though it's not in a loop. It's part of the delay. It's one cycle, but it's the difference between a really nice looking number and a really gross looking number. Other questions? This was about as hard as I would expect because there's 3 levels of nesting. All right, but it shows clearly what has to happen at every point. All right. What else can we do? We got about a half hour left, so plenty of time.
Can you go over when to use LDS and out?
That's it?
And then there's like SDS versus this.
Well, LDS, STS, in, out, in, right? So LDS is analogous to out, STS is analogous to in. They both do the same thing. If you look at their mnemonics, LDS, RD, K16, out, wait a minute, that's swapped. Wait, that's wrong. No, so that's your first thing. LDS loads from memory into the CPU, which means it's in. Okay, so it's not LDS versus out, it's LDS versus in. And STS is out. It has to do with the direction of the CPU. If this is the CPU, and here's memory, and here's I/O space, if data flows from the I/O space into the CPU, that's in. If it flows from the CPU to the I/O space, that's out. Same with memory. If you've got memory and it goes into the CPU, you're loading into the CPU. You're loading out of memory. Here, you're storing into memory from the CPU. Okay? That's first thing. Now, in this diagram is the answer to your question. When do you use LDS and STS versus in and out? Well, LDS accesses memory, SRAM. In and out access I/O space registers. Okay, I/O space is part of memory space. This is all of memory. Here's 0, here's FF, FF. Between 0 and 31, those are your general purpose registers. Okay? That is, by the way, 0 to 19 hex. Starting at 20 hex, we have I/O space. That goes on for some time. Then after I/O space, we have extended I/O. And finally, at address 100, we have SRAM until the end of SRAM. And then this is unused space down at the end, but it's 16 bits. Okay, so if you want to access any of this space here, you use LDS, STS. If you want to access just this little section right here, this is in and out. That's it. Okay, so what is in I/O space? Well, the register summary sheet comes in handy there. The only thing we know about that's in I/O space, we know about our I/O port registers, port, pin, and DDR. We know about our status register, and we know about our stack pointer, SPH, SPL. That's all we know about in data space, or sorry, in I/O space right now. There is other stuff, and after the first exam, we start talking about things like timers and communication peripherals that deal with this stuff a lot. But that's it. LDS and STS just access anything in SRAM or extended I/O. We have not talked about a single extended I/O register yet, as far as I know. Okay, we've only talked about I/O registers. So if it's a register with a name, in this exam, it's probably I/O. If it's just a number, chances are it's SRAM. Now, the way in and out work, it goes from 20 to 5F, right? So extended I/O starts at 60 and goes to FF. Okay, but in and out themselves actually use address 0 through 3F to talk about the address. You use an I/O address. Okay. So most of the time we never see that because we just use the mnemonic for the register we're talking about. We use pin C instead of, if I quickly look one of these up here, it's 20 hex is the difference. So I'm looking this up here. You can't see this, but address 23, 20, 21, 22, 23. That is the pin B register. Pin B. But we don't address it as 23. We address it as 03. That's the I/O space address, the I/O address for pin B. Okay? So when you're looking at a disassembly view, it's going to show 03. Say in or out 03. That's the only difference there. Even though it's listed as 20 through 5F as a data space value, I/O instructions use the I/O address, which is just the same address, the data space address, with 20 hex subtracted from it. So 20 becomes 0, 5F becomes 3F, and that's it. Okay? The fact that the general purpose section goes from 0 to 31 is not an accident. We have 32 general purpose registers. Okay. So technically you could use LDS if you wanted to access these memory locations here, 20 to 5F, but it's much easier to use in and out because LDS and STS take 2 cycles, whereas in and out each take 1 cycle. Okay, I think that's all I can say about in and out versus LDS and STS. What else can we talk about? What about loading from program memory? Okay. Remember, we have a architecture that we use. And the architecture says that we have memory over here, and we have ROM over here, and they have their own bus. There's a separate bus. What do we call that kind of architecture? It's Harvard architecture. There's a split right down the middle. So anything that we want to store, any kind of constants or strings or anything like that, that we want to store need to be stored in ROM. Was that a question or just a... That was just a bug. So there's one instruction, LPM, that allows us to get data from flash ROM and put it into the CPU. But there's a whole lot going on with this instruction that causes people a whole lot of headaches. First off, it's an indirect addressing mode, which means you have destination register and then an index register. So the index register Z points to somewhere in ROM. So the CPU goes to Z, and then Z goes to the ROM, and then the ROM goes directly back to the CPU. So it's an indirect addressing mode. We say, oh, what you need to get is in Z, and then you need to take wherever Z is and go there. So it's 2 steps. It's indirect. And we could do a Z+. LPM only works with Z, not X, not Y, just Z. Furthermore, it gets more complicated. Because when we have a label, .cseg org 50 data dot db define byte 5, 10, 20. We've just defined 3 bytes in program memory at address 50. The problem is program memory is 16 bits wide, which means it's 2 bytes. So over here at address 50, we store 5 and 10 and then 20, like so. And this one's kind of unused. LPM lets us access individual bytes, but data, the label, okay, is 50. Everybody, I think, can see that I said .org 50, so there it is, 50. Everybody's happy with that. Data is 50. Okay, that's not the address I need to load from. LPM doesn't take 50 to get the number 5. It actually takes 100, and here's why. At address 0, there are 2 bytes. If we were to number them, it would be byte 0 and then byte 1. At address 1, it's 2 and 3. At address 2, it's 4 and 5. In fact, the start byte, the high byte of any program memory location, is actually the double of that. So this byte at 50, it's actually address 100, 101, 102. So we need to get into Z the number 100. And I think you can do that at this point. LD, WI, ZH, ZL, 100. And that's it. That puts 100 into Z. And then we can say LPM R5, comma, Z. And that will get the 5 in this example out. But what if you didn't know where that 5 was located? What if I didn't give you this thing here? I just gave you CSEG data, done. You'd have to use the label. You'd have to use data in some way. Now, data is equivalent to 50. So how do I get 100 from 50? What mathematical operation do I use to turn 50 into 100? Did you say divide it? Divide it by what? You got one chance here. Divide it by what?
I didn't mean to say that.
Well, but you could divide, right? What could you divide it by to get 100? 50 divided by what is 100?
0.2.
Phone a friend, quick. Yeah, dividing by a half is the same as multiplying by 2. But let's just, rather than going that long, complicated route, let's do it this way. Instead of saying 100, we're just going to say data times 2. You have to do it like this. You have to. It's the nature of the fact that it's a 16-bit wide address space. Okay, so data points to the location 50, which is the 100th and 101st byte in program memory. Most programmers don't write it this way, however. Okay, yeah, we don't say data times 2. We say data shifted left by 1. It's the same thing. It's exactly the same thing. Data shifted left by 1 is the same as multiplying by 2. It's more of a convention. Okay, but that's it. Now, LDWI, if you want to use it on the exam, you have to write it somewhere on your exam. Okay? So you can't just use it willy-nilly unless you show me you know what it means. If you want to just have a scrap sheet of paper, that these are all the macros that I intend to use, you're free to do that. You can write them once on that scrap sheet of paper, and you attach it to your exam. For those of you who haven't had an exam with me, you write only on one side of paper. Doesn't matter if it's a piece of scrap paper or an exam page. One side. I don't grade stuff on the back. I will not listen to any sob stories. Oh, but the answer was on the back. I don't care. It's a very simple thing. If you need scrap paper, we've got reams of paper that you can use, okay? So anytime you need scrap paper, you just walk up to the front of the room, you get the paper, you come sit back down. That's it. All right, so you can have as much scrap paper as you want. Put your name at the top of every piece of scrap paper. Make sure that there's a number associated with each scrap paper. Okay? So we've talked about a lot of macros. I know in the lecture slides, I put a bunch of them up for you. I know we did a lecture where I went through a bunch of my favorites. All right? They're all designed to let you write what you want to do, not how you want to do it. So I want to get something into Z. All right, there it is. Boom. Then I want to load from Z. Done. For the next lab, lab 3, you're going to be doing a lot with this. Okay, so keep in mind that that lab is coming up on Thursday, I think, right? Okay, how many people have looked at that lab? Might be in your best interests. Like, it's coming. All right. Other questions? 1 and then 2. Shifting. There's a song. Step to the left. Step to the right. That's all shifting is. You take a number. Let's take a random number. There it is. Slide to the left. It slid to the left. Slide to the right. What do we do with those empty spaces? For shifting, we fill them in with zeros. Every time we interpret them as if the radix point was to the left of the rightmost number. So this number in hex would be 2b. This number in hex would be 5, 6. This number in hex here, this guy goes away because we shifted him to the right. So there's nothing beyond that. It goes away. So this would be 1, 5. That's it. That's all there is to shifting. That's shifting over by 1. If you want to shift over multiple places, take this number, 1, 0, 0, 1, 1, 0, 1, 1. Shift it over 2 places. It's really just moving the decimal place over 2 places. These guys go away at that point. Gone. So this is your new number. So instead of 9b, you now have 2, 6 hex. All you got to do is move that binary place around.
So if you loaded a number into the register and you shift it,
You're talking about this question. LDI R7, comma, 1 shifted left by 5, ORed with 1 shifted left by 3 from last year's exam or something like that? Yeah, okay. So this is fine. This is 1 shifted to the left by 5 places. So shift it to the left 5 places. Here we start. 1 place over, 2 places over, 3 places over, 4 places over, 5 places over. We fill in the remaining things with 0. Did I do that right? 1, 2, 3, 4, 5. That's it. So there's the number shifted 5 places over. So 1 shifted left by 5 is binary 1, 0, 0, 0, 0, 0. 1 shifted left by 3 places. I want you to notice if I take a 1 shifted over by 5 places, how many zeros do I have? I have 5. So 1 shifted over by 3 is 1 with 3 zeros. This symbol right here means bitwise OR. So you take 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, and OR them together bitwise. What's 0 ORed with 0? 0. What's 0 ORed with 1? What's 0 ORed with nothing? 0. What's 1 ORed with nothing? 1. That's it. So then you could interpret that as hex or decimal or whatever you felt like. But shifting all alone, that's it. You guys don't have to feel ashamed if you got last year's exam and you want to know how to do a problem on it. Just ask me. Say, I want to do this problem. Yes?
Can we go over how to change a line code to
Sure. But if someone could lend me their ASM sheet. So I'm just going to pick a random line, something like about here. Subtract immediate from word. SBIW. R7. Oh, can't do R7. R17. 10. I made it up. Just picked one at random. Subtract immediate from word. To turn that into an opcode, we first have to know what the opcode is. And as I read across, this is 1001, 0111, KK, DD, KK, KK. So what's the first problem that I encounter here? Look at the notes on subtract immediate from word. Yeah, you can only use 24, 26, 28, and 30. So actually, this is invalid. All right, well, that was a simple question. Invalid. Assembler error. You can't do this. All right, fine. Let's rewrite this. Let's write a valid one. SBIW R2610. Now, what this really means, if you look at the operation, is R27, R26 is going to take on the value of R27, R26, meaning concatenate those two registers together, minus K. So let's solve for K first. We have a total of 6 bits of K. So we take our value here and convert it to binary. 10 is 1010. We have to fill a total of 6 bits, so we fill up. There it is, 6 bits. So now we know at least the fixed values are going to be 1001, 0111. The K bits are going to be 001010. Now DD is the last piece. How do we turn R26 into 2 bits of D? Well, look back at the note. What can we use? We can use R24, R26, R28, R30. Now, what are the possible values of DD? DD is 2 bits, so it could be 0001, 1011. We've got 4 possible inputs, 4 possible outputs. What's the simplest way to map the inputs to the outputs? About like that. Right? So R26 is going to be what? 01. So all told, this is going to assemble to 971A. And that's it. All you have to do is take anything else. Somebody want to do another one? Let's do let's do a good one. Like let's do one more. Skip if bit in IO SBIC, pin B, comma 5. So this says skip the next instruction if the 5th bit of pin B is cleared. So first thing we have to know is what is the I/O address of pin B, which I coincidentally mentioned, 10 minutes ago. Pin B is located at data space address 23, which makes it I/O address 3. So if you do need to do this for an I/O type instruction, you need to know what the I/O address is. So you may want to bring that register summary with you. So SBIC 1001. Just make sure I'm reading off the right row here. Yep. 1001 again. A, B. Okay. So A is the I/O space address. We know that that's already a hex 03. 5 in binary is 0101. So we know our fixed values, 1001, 1001. A has to be 3. What is 3 in binary? Yeah, 1, 1. So everything else is just zeros. 5 is going to be 101. So you read this off in hex and you end up with 991D. That's all there is to it. Every time you just look at the arguments, they're generally positional. Okay. Let's, you guys want to try one on your own? I'll give this back to you. Move R17, R5. Take a shot at that one. Shouldn't take you more than a minute. Oh, my head is right there. You all done? You want to read me out what just the opcode says?
0010
Okay. All right. So first thing we know is the fixed values 0, 0, 1, 0, 1, 1. RD is 17. 17 is going to be a 16, no 8s, no 4s, no 2s, and a 1. R5 is 1, 0, 1. And I know that I have 1, 2, 3, 4, 5. So that's 5 bits worth of R, 5 bits worth of D. R, D. So how do I fill these in? Well, the first bit of R appears here. So I'm going to take the first bit of R and put him here, 0. D is contiguous, so So I'll put him here. 1, 0, 0, 0, 1. And then I have the remaining bits of R, 0, 1, 0, 1. So R is a split operand. It's a split operand. It exists in two different parts. There are lots of instructions that do that. They have their operand split inside of the opcode itself. Okay, so that's it. That's all you had to do. So all told, this would give you an opcode of 2D15. All right, we got time for one more question. I mean, iteration is going to be part of it. Iterate over memory, iterate, do something. Sum it, move it, copy it, overwrite it, add 1 to every location. It's going to be do something to a block of memory, probably. Like maybe just put it all as zeros, put it all as ones, put it as an increasing sequence. Put it as an increasing sequence, not starting at 0. Start at 15 and fill it up. Okay? But almost certainly it's going to involve a loop. If you think that you can write it by doing a bunch of LDSs and stores, I'm going to make it so you have to write 5,000 lines to make it work. All right? So just figure out how to do it with a loop. You'd be better off. And if you're looking at the problem and you're going, this doesn't need a loop, ask me. Maybe it doesn't. Maybe I've tried to pull a fast one on you. There's no harm in asking about a question on an exam. I don't judge you on an exam. It's stressful enough. Just ask me. Whatever you want to ask. Whatever pops into your head. All right? No judgments. All right. Please pick up your homework as you leave, and I will see you on Thursday. Anybody who has a Center for Access and Success thing, just see me. Make sure that I have your form before you leave today, because I'll put you in a separate space, okay?